Hello and namaste everyone. Welcome to lecture 38 of this NPTEL course on stochastic approximation. In the last week and also in this week, we have been looking at two variants of the general stochastic approximation algorithms that we had studied in the beginning of this course. Right. So, in particular we focused at two time scale stochastic approximation and stochastic recursive inclusion, and in particular we looked at the problem of solving a linear system of equations where some of the measurements come from adversaries. Towards that we had designed algorithm, right, based on the stochastic gradient descent with respect to the L1 norm of Ax minus expected value of y, right. And in two classes before this we looked at the differential inclusion that governs its limiting dynamics and showed that all solution trajectories of this differential inclusion indeed converge to expected value of x. And in the previous class we said that we are now going to analyze the behavior of the stochastic recursive inclusion algorithm itself, right, and we said we will make use of this Robbins Siegmund theorem to prove this result. In some sense this is a different strategy to prove this result. We could have as well used the generalization of ODE method also to prove convergence, but I felt that the Robbins Siegmund method is easier for the proof of this result, and that is what we started discussing from the previous class. And in the previous class we stated the Robbins Siegmund theorem and derived a partial inequality, and in this class we will take that partial inequality further and eventually be in a position to apply the Robbins Siegmund theorem and use that to show convergence of xn. So, let us begin with the formal details, right. So, as I said we started looking at the convergence of the following algorithm, and we said that H has a particular form, this epsilon n and mn plus 1 have suitable forms. In particular this is a martingale difference sequence, right, and we wanted to make use of this Robbins Siegmund theorem which I had stated in the previous class. And so far what we have done is we have showed that this quantity over here is upper bounded by this term plus this term plus this term plus this. Okay. So, this was the bound that we had obtained, and there was one more term that involved your mn plus 1, right, and that term we managed to show goes away because it is a martingale difference term, right, and hence we were left with only these expressions. And what we will eventually do is we will choose a step size which satisfies alpha n square is less than infinity, right, and this will take care of this term. So, we do not have to worry about this term, and what remains to take care of are these two terms, right, and in today's class we will see how to deal with these expressions, right. And in the previous class we had made some initial effort towards obtaining a bound on the second term, which is the term that is present over here, right, and we had obtained the following intermediate lemma which we said we will use to bound this second term. So, what this intermediate lemma said was that suppose eta is defined in the following way, and let us say k is defined with respect to eta in the following way, right, then for any s which is a subset of the number of the row indices of your matrix A which correspond to the coordinates of your y vector, right, such that cardinality of S is q, then such an inequality holds, right, and we said that this inequality is saying more than what was presumed about the matrix A, right, and while we had proved this inequality in the previous class we had presumed that this eta was strictly bigger than 0, right, and what we will do today is we will first show that this eta is greater than 0 and then see how this result of ours can be used to obtain a bound on the second term. So, recall that eta is defined in the following way. In particular you can see that there is a norm x that is sitting here, right, and you have a summation that is over here, right. So, and we have also presumed that x is not equal to 0. So, we can take this norm x inside, and if you look at x also keep in mind that because of the linearity property of your absolute value, right, you can I should not say linearity property, but what I should say is that for the absolute value for any real number r, c times r is absolute value of c times r, right. So, this is true, So the C that is over here is being played by this norm of x, so I can take it inside, right, and wherever I have this AJ transpose x, I will now have AJ transpose x by norm of x, right. So because I have this expression over here, one can imagine this to be a unit vector, right, and hence this definition can be modified in the following way. So observe that here, instead of just considering x not equal to 0, we can restrict our attention to all those x where the norm of x is 1, and we drop this norm of x from the definition, right. So we have this expression now. Is this okay? Now whatever is there inside, right, let us call it as phi s of x. So phi s of x is basically 1 over n times this summation minus this summation, right. Now since we are taking the min over x such that norm of x equals 1, let us collect all such x's, and it is easy to see that this x is a compact set. It is compact because it is closed and bounded. Furthermore, this phi x of x is a function that is continuous in x, right, and because of this reason, I mean the fact that we know that any continuous function on a compact set achieves both its maxima and minima, and for us what is relevant is the fact that this function achieves its minima. Achieves its minima means that there is a specific point x prime lying in the set, that is the Euclidean norm of this x prime is 1, and phi s of x is greater than phi x of x prime for every other x, right. So for every other x, so that is what we mean by achieves its minima, right. So often there will be the minimum value of phi of x, but there could be no value that achieves it. Is this okay? But since we have a continuous function on a compact set, one can conclude that there exists some x prime such that this inequality holds. Is this okay? However, we know that for S such that cardinality of S is q, this relationship is greater than this for any x which is not equal to 0. In particular, this relationship holds for x prime, and hence one can conclude that your phi of x prime is actually strictly bigger than 0, right, and since it is strictly bigger than 0, one can conclude that for any x in this satisfying norm of x equals 1, your phi of x is bigger than equal to phi s of x prime, right, and this quantity we have already shown is strictly bigger than 0, right. And since the number of s such that cardinality of s is q, and we know that if you take the minimum of strictly positive numbers which are finitely many in number, then the minimum will also be greater than 0. From this one can indeed conclude that this eta is actually strictly bigger than 0, right. So what we managed to show is that this quantity over here, right, is upper bounded by some specific quantity that is strictly bigger than 0, right, and that could depend on s, but since the number of such s's is finite, right, this whole quantity is guaranteed to be strictly bigger than 0, which is what is the definition of eta, and that verifies what we wanted to show, which is that eta is strictly bigger than 0. Is this okay? So now let us see how we can use this result to obtain a bound on the second term. So recall our goal is to obtain a bound on a term of the following form, right, and towards that let us first recall what h of x comma y is, right, and h of x comma y is as given over here. In particular, for I in A complement you presume that you have the ideal update, and for I in A, which is basically the set of coordinates which are governed by adversaries or controlled by adversaries, okay, this can be an arbitrary value, okay, the sign expression can be arbitrary value and it is controlled by the value of y. In particular, it is controlled by the value of y of I, which is given by your adversaries, right. So now if you take the inner product of x minus expected value of x transpose h of xy, right, in one of our previous classes we had shown that this expression is upper bounded by minus of sum of I in A complement, the absolute value of ai transpose x minus expected value of y of I, right, and plus, okay, so here because the signs are controlled by adversaries, we do not know what this sign value will be. However, if you take this expression and take its inner product with this, one can again show that we would end up with an upper bound like this. Okay, so notice that for I in A complement we have a negative sign, but here we are considering the worst case behavior of your adversaries, hence this upper bound comes into play. Right, and in this intermediate lemma that we had shown, right, therein we showed that for any x, right. So let me take you to that result. Okay, so the result over there showed that for any x, k minus 1 times this summation is bigger than k plus 1 times this summation. So in place of x, if I replace this with x minus expected value of x, one can see that we will end up with an inequality of the following form, right. So I have just, wherever x is there, I have replaced it with x minus expected value of x transpose, and we will indeed get the inequality of the following form, right. And now what we are going to see is what does this inequality tell for an expression of this form, right. So what we are going to do is, from this inequality we are going to rearrange terms so that we get an expression that looks something like this. So towards that you can see that there is a minus some I in A complement absolute value, right. So that minus 1 is sitting over here, so we retain it as it is, right. And what we sorry, I should be careful, I mean this term will appear on the right hand side. So what we do is, towards getting the term on the right hand side, the k times this expression we move towards the right hand side, and you can see that this expression mirrors what you have over here, right. And this minus 1 led to this expression, and you can see that there is a plus 1 with this expression with I in A. So if you bring it to the left hand side, everything will be with a negative sign. So the left hand side will basically be I in A and I in A complement, which basically forms your complete index set. Hence the left hand side, because of this minus 1 and this plus 1 being moved to the left hand side, we will end up with minus summation I equals 1 to n, the absolute value of this quantity over here, right. And the k times this expression I have moved to the right, so you have k times this negative expression, and whatever is the plus 1 over here I retain it as it is, and now this k I have taken out in common. Is this okay? And one can now see that this expression that you have, okay, this expression that you have is precisely what you have over here, right. And if I multiply by 1 over n on both sides, one can see that I will end up with minus 1 over n, right, and k over n, right, and whatever is this expression, and as I told you, this expression is precisely x minus expected value of x transpose h of x comma y. Now the question is, what happened over here? Well, if you see here, I have I equals 1 to n, the absolute value of this. Well, this is precisely the L1 norm of Ax minus expected value of y, right. This is, you can see that this expression is precisely this expression, and hence we end up with a relation of the following form, that is k times this inner product, right, is less than equal to minus of this expression. So if you remember, we were working or trying to derive an upper bound on this quantity, right. So this, we had this expression on the right hand side, this expression on the right hand side, and this expression. Furthermore, we had this expression on the right hand side. Now what we are saying is that we are going to replace this quantity, right, by this expression and with a k in the denominator, right. So alpha n times this expression was there initially, now we are replacing it with a negative of this L1 norm by k. Is this okay? So this is the expression that we have. So whatever is the second term, we have now managed to obtain a bound. How this bound will be useful, we will soon discuss. In particular, if you remember the Robbins Siegmund theorem, the Robbins Siegmund theorem said that suppose you have something like expected value of x n plus 1 given fn, this is less than 1 plus a n xn, okay, minus bn plus cn. So you can see that there is a negative Bn term that sits over here. So that role is being played by this quantity over here, right, and now it remains to bound an expression of the following form. Now let us see how we can bound an expression of the following form, right. Now towards obtaining a bound on this, first let us recall the description of epsilon n. So epsilon n, recall, is 1 over n plus the difference of sum of differences of signs. In particular, this sign included the idealized expected value of y, and this included what we have at time n. Is this okay? So we tried comparing this sign expression with this sign expression and multiplying this whole expression by a of I, right, and the nice thing over in epsilon n is that this I is in a complement, which means that every I over here corresponds to an honest sensor, which means that as n becomes larger and larger, indeed this yn will converge to expected value of y. However, just because this converges, the sign expressions need not converge, right, obviously, because it is not a obvious matter of fact, because sign is a discontinuous function, right, and we need to take care of it, and we will see how to deal with that. Okay. So towards obtaining a bound on the sign expression, what we will do is we will first make use of a relation that we discovered, right, that exists between sign of numbers of such form. So let us first understand what do we have over here. Suppose R1, R2 and R, let us say, are 3 real numbers, right. So since they are 3 real numbers, I hope you agree that if I try to draw the real line, you could have maybe R1 here, maybe R2 here, maybe R here, and maybe in a different scenario, right, your R could be sitting over here, or maybe in a different scenario, right, R could actually be here. So in other words, your R1, R2, R, right, they could come up in different orders. Now whatever be these possible order, one can see that whatever is the arbitrary value of R1, R2 and R, it always satisfies the inequality sine of R1 minus R minus sine of R2 minus R is upper bounded by 2 times, okay, 2 times the indicator that R1 minus R2 is bigger than R minus R2. So you can consider maybe such an ordering and verify that such an inequality indeed holds. Is this okay? Right, and recall that this sign expression either can be -1, +1, and if the argument is 0, right, in which case it can take an arbitrary value between -1 and +1. So one can see that in all those scenarios one can indeed verify this condition over here, right, and because this inequality holds, one can show that this xn minus expected value of x transpose epsilon n is upper bounded. So this 2 comes from that inequality that we had, 2 over n times summation I in a complement, and if you recall we had so x minus x transpose times ai. So this expression will lead to something like this, and I should perhaps put an absolute value over here. So this absolute value is upper bounded by this, and this is why you have an absolute value over here, and then you had the difference of signs, and the difference of signs leads to an indicator of the following form. So you can check from the previous slide why this indicator sort of makes sense, right, and we end up with an indicator of the following form. And then my PhD student Shweta Ganesh realized that this expression that you have, since it is upper bounded by this, we can use this inequality that is sitting within the indicator to upper bound this quantity over here. So that leads us to a bound of the following form, that is 2 over n, we retain it as it is, and wherever you have this expression, because we have an indicator here, I will replace this expression with what you have over here, that is what I have written here, and hence we have this upper bound. And now I drop the indicator, because indicator is upper bounded by 1, I drop that indicator, and finally one can show that the absolute value of this quantity is upper bounded by the quantity that we have over here. Is this okay? Now what we will do now is to get an upper bound for this quantity over here, and towards that we will make use of what is known as the law of iterated logarithm, right. I encourage you to look it up. And now let me first try to tell you why the law of iterated logarithm sort of becomes natural here. So notice that here we have I in A complement, which means that your I is not related to your adversarial measurement, right. It is actually given by honest or a non-adversarial sensor, right. And hence for any I in a complement, recall that yn plus 1 of I, right, has this following update rule: yn plus 1 of I equals yn of I plus beta n times some expression like this. Now if I substitute for beta n, so now I am actually choosing a step size choice. If I choose something like 1 over n plus 1, right. So if I choose a step size of the form 1 over n plus 1, then one can see that your yn I has an update rule of the following form. I think there is some typo here. This should be n times some so there is a issue here. So this should be k. Okay, there is some mistakes here. I am sorry about that. This should basically be I. This should be k. So you should have n times summation k equals 1 to n calligraphic yk indicator ik equals I the whole by n. So what I am basically saying is that if you have an update rule like this and your beta n is actually of the form 1 over n plus 1, then one can show that this update rule is basically averaging the samples that you have over here across different time instances. Okay, so this is your little y and this is your calligraphic y, which corresponds to the sample that you have obtained. In other words, your little yn is basically doing an averaging of the samples that you have obtained at every time instance, right. Now because of our assumption, okay, these random variables that we are using over here are independent and identically distributed, right. And in particular, if you take yn of I and subtract it with the expected value of y of I, then one can show that because of the presence of n over here, okay, you have 1 over n and this sum of random variables of the following form, and this random variable one can easily show is of 0 mean, right. And if you define sigma square to be the variance of this quantity, then from the law of iterated logarithm one can show that if you take the absolute value of Sn, so Sn is basically the sum that is sitting over here, and divided by sigma, and in particular you divide it by the square root of n times log of n. So here is where you see this iterated law of logarithm, right. So if you take the lim sup of this quantity, then the law of iterated logarithm says that the lim sup of this quantity is going to be 1 almost surely, which means that eventually these two numbers will go towards will be upper bounded by 1, right, because of the lim sup that is present over here, right. And from this result and the fact that here you have Sn over n, right. So this is basically Sn over n, right. So if I take Sn over n and write it as Sn over square root n, square root, so this n I have written it as square root n times square root n, and then what I will do is I will multiply and divide by square root log n, right. And what we have been told is that this expression, okay, so let me put it in red. So this expression will basically be upper bounded by a constant asymptotically, okay. So that is what we have been told over here, right. And this constant could depend on the sample path, that is on one sample path the constant could be 5, in another sample path it could be 1000, and so on and so forth. So on different sample paths you would have different constants, but nevertheless it will be a finite constant, and one can make use of this result to show that your yn minus expected value of y of I, which is your Sn over n, is upper bounded by C of I times square root of log n over square root n, okay. So from the law of iterated logarithm one can show that this indeed holds, and I would like to again emphasize that this constant could be sample path dependent, right, and one can then show that 2 times alpha n xn minus expected value of x transpose epsilon n, if you remember we had shown it to be 2 over n alpha n times this summation, and now using the law of iterated logarithm we have shown that this quantity over here is upper bounded by some constant times square root of log n by square root n. Now if you define C to be the max of I in A complement C of I, you can pull this off, right, and since there are n minus q quantities in A complement, right, we will have A minus n minus q over here, and then we will have square root log n by square root n, right. So the key thing that we have to keep in mind is alpha n square root log n by square root n, right, and now what we will show, what we have managed to show is that this conditional expectation is upper bounded by xn minus expected value of x square minus 2 alpha n times the L1 norm of this quantity, right, and we had 2 alpha n which was sitting over here. I think I should say that this will lead to a 4, okay, this also should be replaced by a 4, right, and because of this 4 over n n minus q c alpha and this, I have written that expression over here, and then we had this a star times alpha n square. Is this okay? A star square times alpha n square, right, and now one can see that this expression that we have is indeed of the form that is desired to invoke the Robbins Siegmund theorem, right, and in the Robbins Siegmund theorem we require that this quantity also be finite, right. So I will treat this whole quantity as the term that we require it to be finite. So we now require that summation n equals 1 to infinity alpha n square root log n by root n to be finite. Is this okay? So if I want this expression to be finite, one can see that if I pick alpha n to be alpha n to be n plus 1 to the 1 to the power half plus epsilon, I think alpha n may be I think there is a n plus 1 missing over here, maybe one can do the calculation appropriately. So if I choose this alpha n to be 1 over n plus 1 raised to half plus epsilon, then one can see that if I take on the one hand this summation alpha n square will be less than infinity, which is the term that is sitting over here. On the other hand, this alpha n root n square root of log n, this will also this alpha n over root n will lead to a term of the form 1 over n raised to 1 plus epsilon, right, this half plus epsilon, and you had this square root n already sitting, so this already contributes n raised to half. So together we will have n raised to 1 plus epsilon, right, and because we have chosen this epsilon to be greater than 0, one can show that this sum because it is of the form 1 plus epsilon, this is less than infinity, and hence one can use the Robbins Siegmund theorem to conclude that xn minus expected value of x converges, right, which is what you have on the right hand side. The square converges and hence the square root of that, which is this quantity, this converges. Furthermore, whatever you had over here, if you take their sum, okay, that sum should be less than infinity, right, and this quantity I hope you agree, okay, can be written as a times xn minus expected value of x, we can write it this way, and then you will have this L1 norm. Right. Now if we presume A has full column rank, which means that this product is 0 if and only if this quantity over here is 0. So by making use of this fact, one can show that this being finite and this converges together imply that the limit should be equal to 0, right, and the way to verify this is the following, that if xn minus expected value of x doesn't go to 0, right, then that would imply that your xn minus expected value of x goes to some positive value, right, and because it goes to a positive value, one can show that this quantity will also be a positive value, but we have presumed that your summation alpha n is actually infinity. So if this converges to a positive value, one can then show that this sum will be infinity violating this condition. So, in other words, because you have that summation alpha and this quantity is less than infinity, and the fact that this converges together, that can only imply that this difference should go to 0, which in particular implies that xn goes to expected value of x almost surely. Okay, so this brings us to the end of our discussion. So, let me quickly summarize what we have done, right. So, in this 2 weeks we looked at 2 time scale stochastic approximation, stochastic recursive inclusion, right. In particular we looked at a scenario where we wanted to solve a linear system of equations where some of the measurements come from adversaries, right, and because they come from adversaries, instead of trying to minimize the L2 norm, we focused on minimizing the L1 norm of Ax minus expected value of y, right, and that led us to some update rule, and then what we said was that if A, your matrix A, satisfies some conditions, right, then by looking at the this behavior of the stochastic recursive inclusion from the perspective of this Robbins Siegmund theorem, one can show that if A satisfies that condition, right, which is that of full column rank, and the fact that your for any k, right, your summation I in k absolute value of AI transpose x is less than summation I in k complement absolute value of AI transpose x. So, if that condition is satisfied, then one can show that your stochastic recursive inclusion will also converge to expected value of x almost surely, right. So, one can see that this algorithm then becomes robust, that is, even in the presence of adversaries we are able to show that this algorithm converges to expected value of x, which was what we wanted to recover, right. And just to highlight, the set valued nature of the algorithm came into play because each time your algorithm visits a specific value x, the adversary has a choice of values, right, to play, and in general, okay, this leads to the set valued nature, right. And if I want to quickly remind you why we wanted to look at xn and yn separately, right, in particular why we wanted to look at different updates, one with xn and other with yn, was that we wanted the expected value of y to sit within the sine function, and unfortunately if we plugged in directly the samples of y, and because the expectation and sine cannot interchange naturally with each other, we had to make use of a 2 time scale algorithm. And again the last thing I would like to highlight is the choice of step size that we made. Observe that beta n is 1 over n plus 1, and the step size choice alpha n that we made was 1 over n plus 1 to the power half plus epsilon. So, you can see here that alpha and beta n are of different orders, which is what brings in the 2 time scale nature. Okay. So, this completes our discussion on 2 time scale stochastic approximation and stochastic recursive inclusion, right. In the next couple of weeks we will be looking at various applications of stochastic approximation. In particular we will look at some applications in the context of reinforcement learning. Until then, goodbye and thank you and namaste.